let's look into the second part of this spin splitting video, whereby we will see what are the reasons behind the splitting of signals, NMR signals. Okay, so just consider a scenario where you have a proton here, here you have two different types of proton, HA and HB, in a different chemical environment as suggested by the substituents here, which are different than the substituents here. Now we know that when there is a nucleus which is subjected to an external magnetic field B0, the nucleus arranges itself either with the magnetic field or against the magnetic field. And in case of a proton, and in case of a 1H proton, this proton gets either arranges with the magnetic field or against the magnetic field. Also, whenever there is an electronic cloud surrounding the proton nucleus, then this also generates a magnetic field of its own, which opposes this external magnetic field, applied magnetic field, and resultant. So the nucleus effectively gets a magnetic field which is B effective and which is lesser than the applied magnetic field. This is the normal NMR theory. Now, when the same nucleus now has adjacent nuclei, NMR active nuclei, suppose here we have proton B. Now this is also NMR active. Now this is also NMR active. Now if this is HA and this is HB, so already it is experiencing a magnetic field which is B effective in presence of an externally applied magnetic field of B0. Now what happens is, whenever there is some NMR active nuclei, so this in a place which is nearby to it or adjacent to it, this nucleus senses the adjacent magnetic field. Just like when you are sitting in a classroom, you are more affected by the person who is just sitting next to you, and are not bothered about person who is far away from you. The person who is sitting next to you will either give you will be a pleasurable company, or it will be not pleasurable in the sense. Okay, so while thinking like that, so now this magnetic field will either enhance the effective magnetic field or oppose the magnetic field. How? Because with respect to this proton, we are discussing this for particular proton, this proton can either arrange itself with the externally applied magnetic field or against the externally applied magnetic field. So when you in your NMR sample, there will be innumerable number of molecules. So consider this here. So now there may be two arrangements possible, and if you see the probability, it will be 50-50%. So here HA and HB, in this case if it is plus half, then it will be arranging itself in minus half. So under the normal condition, a nucleus experiencing a magnetic field B0 will having an electronic cloud and or with all the opposition to the external applied magnetic field, with the effective magnetic field B effective, without the presence of a surrounding nuclei, NMR nuclei, will give a signal somewhere in the spectra according to its chemical environment. So this is supposed to be the original signal. Now whenever there is an external or adjacent nuclei, NMR active nuclei, what will happen is, if this nuclei is arranging itself with the external applied magnetic field, it will try to enhance this external applied magnetic field. That means the B effective now will be more than what it is here. Okay, so if I say this is B dash and it is B effective, in this position B dash effective will be greater than B effective. Okay, so now since it is experiencing more externally applied magnetic field, it is experiencing more magnetic field, that's why the signal will somehow come downfield. If this is 0, then it will come downfield to what it is happening in case of a normal nuclei without any adjacent nuclei. So in this case, since this nuclei is arranging itself in a system which is opposing the external applied magnetic field, V0, in this case this it will oppose the external magnetic field, and now the resulting magnetic field here, suppose if this is B effective dash, then B here, B effective dash will be lesser than B effective, where B effective is the magnetic field where there is no adjacent nuclei here. So in this case, since the external magnetic field experience will be lesser, so then the signal will somehow be in the upfield region. Okay, so under this condition we see that now the signal appears as a doublet. So the original signal has now been split into two, and it acts as a doublet. So if we see here, if we say that your plus half is represented by this sign and minus half is represented by this sign, so with respect to HA, with respect to H, so let me continue here, I think it was not visible. So with respect to HA, the adjacent nuclei, so if I draw it here, with respect to HA, the adjacent nuclei can either arrange itself in positive spin or in negative orientation with the external magnetic field. That's why we get a doublet. That is, and the probability of finding the orientation of the adjacent nuclei in these two possible states is 50% each. So that's why the two peaks are of same intensity. So due to this reason, so for any compound where the adjacent carbon has one NMR active nuclei where n is equal to 1, so now that's why we get, using n plus 1 rule, 1 plus 1 equal to 2 signals, or signals, we get a doublet. Now let us look at a scenario where the adjacent carbon has two proton nuclei. Now in this scenario, we know that using your n plus 1 rule, this HA, suppose this is HB, for HA we get 2 plus 1 equal to 3, that is a triplet. So if you have for HA protons, we get a triplet. Now considering this, if you have the two protons, it can either arrange itself with the external magnetic field or against the external magnetic field. These two protons can either be in plus half position, or minus half position, Also it can be that one is in plus half position, other one is in the minus half position, or it may be such that this nuclei is in minus half position and this is in plus half position. So these are the possible orientations. And if we see the total here, if we see plus half, which is equal to 1, and this is equal to 0, and this is equal to, again this is plus 1, this is minus 1. These are the three possible orientations possible. And if you see here, if in this case, in this scenario, the signal will be this one. Why? Because both the nuclei are with the external magnetic field, and since they are with the external magnetic field, it will enhance the magnetic field that is experienced by this proton, and that's why the signal will be little bit downfield from the original position. And here, if both the nuclei are in opposite spin, so that's why both are now opposing the external magnetic field B0, and that's why the resultant effective magnetic field experienced by HA will be lower than what it used to, and that's why it will go to a little bit upfield position. And here, if you see, one is in positive half, one is in negative half, both cancels out each other, and the signal is in the exactly the position that it used to come in case of the situation where both HB and HBr, these two nuclei, are not present. And if you see the probability percentage, the probability of this having in a system of molecules in the sample, the probability of these orientations of 0, where both one is in plus, one is in negative, is 1:2:1, and hence the signal intensity ratio, where the middle peak is twice as high than the adjacent peak. So that's why this is the orientation, or this is the how the triplet peak is observed. So now let's look at this particular example. So here we know that for HA we get n plus 1. N is equal to number of hydrogens in the adjacent carbon atom, 1, 2, 3. So 3 plus 1, which is equal to 4. So the HA will appear as quartet. And HA for HB, we know n plus 1 is equal to 1 plus 1 is equal to 2, that is equal to, we get a doublet. This will be the spectra for this kind of molecules. Now let us see how the quartet peak appears in the NMR spectra. So since we have now three nucleus, now the three nucleus can orient itself in either all are in positive spin or all are in negative spin, or n you have all in positive, all in negative, 2 in positive, 1 in negative, 1 in positive, 2 in negative. Now for this orientation, it may so be that here you have this, and this is negative, this is positive, or you have this is negative, this is positive, this is positive. And in this case, it may be so that you have this is negative and these two are positive. No, this will not be the orientation for this one. It will not be, it is not correct. We have 2 in negative, 1 in positive, or you have this is in negative, this is negative, and this is positive. So these are the possible orientations. So if you sum it up, you will get that plus half plus half plus half, which is equal to plus 3 by 2, and similarly this is minus 3 by 2, and this is plus half, and this is minus half. So these are the possible magnetic orientation in this for HA. So for HA, if you have to get the spectra drawn here, if you will see that in this case, if this is the original position where a bare nucleus will give this this one signal, then you have a signal here, and you have a signal here, then you have a signal here, and you have a signal here. So we get a quartet. And if you see the probability or the probability of these orientations, it will be 1:2:2:1, or it's not 1:2. No, it's not 1:2:2:1. It is 1:. So the probability is 1:3:3:1. That's why the peaks are this is 3 times more than this one. Similarly, this is 3 times more than this one. So we get 1:3:3:1 peak. So the intensity of the peaks for different doublet, singlet, doublet, triplet, quartet, pentet, and can be given by your Pascal's triangle, where you have 1, then 1, 1 plus 1, 2, 1, then 1, 1, 1 plus 3, 3, 1, and you have 1, 4, 6, 4, 1. So by this way, so if you have 1, so that means you have 1 peak, you have 2 peaks of same intensity. Then you have, for a triplet, the middle peak is of twice higher. So this gives the probability of the number of orientations of how the atoms are arranged, and accordingly the intensity of the particular peak increases. So I think with this your splitting spin splitting concept is clear, and if you have any doubts, kindly please let me know.